And now for the last of our vitamin series, the fat-soluble vitamins. Fat-soluble vitamins include four, A, D, E, and K. They're found with fats in foods. They require some special handling for absorption, transport, and excretion, and they're stored in the liver and the adipose tissue. So there can be a little bit more variability in intake in terms of developing deficiency. You can really look at average over weeks or months, and then toxicity can be a lot more dangerous. Vitamin A includes two forms, the retinoids, which are preformed, retinol, retinal, and retinoic acid, and carotenoids, which are yellow-orange pigments that can be vitamin A precursors converted to retinoids. Beta-carotene is the classic one that we think about here. Vitamin A functions include cell differentiation. This causes immature cells to change in structure and function to become specialized by changing gene expression, and this is necessary for the maintenance of epithelial tissue. It's also part of rhodopsin. When light strikes rhodopsin, it initiates a series of events that result in a nerve signal being sent to the brain, which then allows us to see, especially at night. Carotenoids can also function as antioxidants. So this is showing the visual cycle here. So first, you see after entering the eye, light strikes the visual pigment rhodopsin, which is in the retina. Then the light causes the retinal molecule to change from a bent or cis form to a straight or trans configuration. Remember those two terms, cis, same side, trans, opposite sides, in organic chemistry, as we talked about fats as well. A nerve signal is then sent to the brain telling us that there's light, and retinal is released from opsin. Some of the retinal is lost from the cycle. Some returns to its original cis configuration and begins the cycle again. When vitamin A is deficient, you can see that regeneration of rhodopsin is delayed, so then light can't be perceived. When we look at that, vitamin A status is really going to determine night vision. So that's why we think of, carrots as helping us see better, right? Vitamin A RDA, 900 micrograms a day for men, 700 for women. Sources, vitamin A in animal products like eggs and dairy, and then also red, orangey, yellow type pigments, and then also dark green vegetables will contain vitamin A in the beta-carotene form because the chlorophyll is blocking a lot of the orange and yellow pigments in there too. Deficiency causes xerophthalmia, which is night blindness that progresses to permanent blindness, also abnormal jaw bone growth in children, and increased infections. Excess intake of vitamin A can cause nausea, vomiting, headaches, dizziness, blurred vision, lack of muscle coordination, birth defects, liver damage, and bone fractures. However, those are all from the retinoid family toxicity. Excess beta-carotene causes hypercarotenemia, which especially when people have pale skin, they don't have a lot of pigment in their skin, they can actually turn a little orange when they eat too much beta-carotene. That's not as dangerous, right? The beta-carotene will eventually turn into retinoids as needed, but if you see a supplement that has high values of vitamin A, they're probably in the beta-carotene form. Vitamin A sources, as you can see, in the retinoid form are going to include animal products, and then in the carotenoid form are going to include fruits and veggies. This is a picture of vitamin A deficiency leading to xerophthalmia. Without vitamin A, you can see there's a hardening and drying of the eye, which then causes xerophthalmia. Vitamin A deficiency is the most common deficiency in the world. And when we look back at the sources, you can see why. So these are pretty expensive sources, right? We're not finding it in beans and grains that can be stored. So in populations where there's not much access to fruits, veggies, and meat and dairy, you might see vitamin A deficiency. Big problem in Africa. And that's a picture of hypercarotenemia. Over on the right, you can see the hand is slightly orange from excessive vitamin A intake in the form of carotenoids. Vitamin D is next. It's made in the skin with exposure to UVB rays. We're only exposed to UVB rays for about half the year. So you really have to be at a certain latitude from the equator to have this happen year round. It's inactive until it's modified in the liver and kidneys. And when we don't have this happening, from around April through October, we're going to need to take in vitamin E from the diet. So these are the different ways that we can get vitamin D. UV rays hit the skin. A vitamin D precursor, which is a cholesterol, turns into the inactive form of vitamin D. Then it's chemically modified in the liver and again in the kidneys. And then vitamin D's role is to act as a hormone. It makes sure that calcium levels stay adequate in the blood so calcium can act as an electrolyte. So it's going to mobilize calcium from the bone if we're not eating enough calcium, or increase calcium and phosphorus absorption from the intestines. So vitamin D's function, in summary, is to maintain normal levels of minerals, calcium and phosphorus in the blood. It also is involved in changing gene expression. So it turns on genes for calcium absorption in the intestines and then turns on genes for bone breakdown as well in the bone. So we really need to take calcium and vitamin D together. It's also necessary for the immune system, muscle function, cardiovascular function, respiratory system, brain development, and has some anti-cancer effects that are just being discovered. The RDA is 600 international units, or 15 micrograms a day. Sources, it's widespread but pretty low in sources in the diet: liver, egg yolks, oily fish, and mostly fortified foods. Deficiency can cause low calcium absorption, leading to rickets in children, which will cause pigeon breast and bowed legs, and osteomalacia in adults, which ends up being brittle bones, very similar to osteoporosis. Excess causes high calcium concentration in the blood and urine, and deposition of calcium in the soft tissues. Vitamin D sources include eggs, salmon, and some milk. It's fortified in milk, so you really need to eat a good amount of fish and some fortified products in order to get vitamin D from the diet. And typically people who live in this hemisphere in the Northeast United States are recommended to take a vitamin D supplement during winter months. And that is a picture of rickets. You can see the bowed legs in that child. And here you see in the dark shaded areas, at those latitudes, we don't get vitamin D year round. So you can see that we're missing out on vitamin D for a good part of the year. If somebody lived, on the Arctic Circle, they would be not getting any vitamin D from sunlight or making their own vitamin D from sunlight at any time of the year. So, you also have different ways, even if you're getting exposed to vitamin D from the sunlight, that could prevent that vitamin D from being made in the skin. That includes sunblock. So any sunblock is going to deplete the reaction from happening because it prevents vitamin D reaction from the UV rays. Or if you're wearing a good amount of clothing, that's going to prevent that from happening too. Vitamin E is next. Vitamin E is an antioxidant. It protects lipids, especially in the membranes of red blood cells, white blood cells, nerve cells, and lung cells. So vitamin E is a little different than vitamin C. It can get inside the cell membrane because of its fat-soluble properties. It also has some anti-inflammatory function, helping with immunity and the regulation of cell growth and death, and detoxification of harmful substances. So what are antioxidants? I mentioned before in my last presentation on vitamin C that they decrease the adverse effects of free radicals. Free radicals are, during aerobic metabolism reactions, oxygen can react with compounds and produce unstable molecules called free radicals. A free radical has one or more unpaired electrons, and an electron without its partner is very reactive. So to regain stability, the free radical quickly finds a stable compound and steals an electron. Now this compound becomes a free radical itself and steals from another, and so on and so on. So you can almost picture this, being a bar on couples night, and a beautiful woman walks into the bar. maybe your current electron is more attracted to her than you and joins up with that free radical, causing you to be frustrated, becoming a free radical, and seeking another electron to pair up with. So antioxidants, you can picture them as sort of being the singles sitting by the bar. They neutralize free radicals by donating one of their electrons. So they have an extra to donate. So when they lose their electrons, they don't become free radicals. They're single, all right? They're not paired up. Free radicals attack and cause damage to the polyunsaturated fats of lipoproteins, DNA and RNA, and proteins. This can lead to cell damage, to disease progression, and also aging. So vitamin E is a little bit of a sketchy antioxidant. It doesn't actually have an electron to donate. So vitamin E does its job inside the lipid bilayer. But when it comes out, all of a sudden it's turned into a free radical because it gave away its electron without having one to donate. So vitamin C always cleans up the mess and brings vitamin E back to neutral. So moral of the story, you really need vitamin C and vitamin E together in order to create a healthy antioxidant status. RDA is 15 milligrams of alpha tocopherol a day. There are other forms of vitamin E as well, and that one specifically is the essential one in our diet. Sources: seeds, nuts, plant oils, leafy greens, wheat germ, and fortified cereal. Deficiency can cause hemolytic anemia in infants. Deficiency is rare in adults, but often we aren't getting quite enough vitamin E for adequate antioxidant function. And large doses can interfere with blood clotting if you're taking supplements, but there's no reported effects from food. And as you can see, food sources are mostly in our nuts and seeds, and they're found, in the oils of most plants. Last, we have vitamin K. It's needed for the production of clotting factors and also synthesizes some protein involved in bone formation and breakdown. So in its clotting factor, damaged tissue causes a series of reactions that involve clotting factors, and several of those require vitamin K for formation. The major one is the conversion of prothrombin to thrombin, which then causes fibrinogen to turn to fibrin, and fibrin are the threads that form the webbing of a blood clot. So without vitamin K, you could see excessive bleeding. So if somebody's on a blood thinner, they probably don't want to consume vitamin K. So something like warfarin, if somebody's on that blood thinner, they're actually told to eat a vitamin K deficient diet because the way warfarin works is it prevents vitamin K from being activated. The RDA is 120 micrograms a day for men and 90 for women. Sources include leafy greens and some vegetable oils. You could see in deficiency abnormal blood clotting that results in some bruising and bleeding. Also reduced bone mineral density, causing fractures. There's no excess reported from food, but large doses could cause excessive blood clotting. And as you see here, sources are going to be mostly leafy greens. Kiwi, green fruit, right, is also a high source of vitamin K. But really, if somebody was on a blood thinner, they would probably want to avoid leafy greens especially. So that makes our vitamin sequence come to an end here. We've talked about the water-soluble vitamins, including the 8 B vitamins and vitamin C, and then finished it up today by talking about vitamins A, D, E, and K. Feel free to review these notes as you look through the vitamin chapter in your book, and also make sure you review the tables on the fat-soluble and water-soluble vitamins, which are found in figures 7.2 and 7.3 in your book.